Okay, so here's where we were last time. By the way, I hope everybody had a good break. Nice long week off. Hope everybody got to relax some. I also hope that, per the email that I sent out, you had at least a couple of minutes to look at a little bit of math so that it doesn't all sort of slip away after a big Thanksgiving meal. And I hope everybody's ready to dive back in. So we are, as you know, behind schedule, so we are going to have to jump right back into it. A quick reminder, though. We started this section with a confession, right? So, I've been playing a little bit too fast and loose with my scalars up to this point in the class. Using complex scalars, even though the definition that we had made of a vector space specifically required scalars to be real, right? And the ways that has come up to this point in the course, to this point here in the course, has been what I'm going to call harmless, victimless crime. All of those bits of sloppiness that I was guilty of were deliberate, of course, but also harmless, right? So all of that stuff can be fixed with no consequences. But not so going forward. So, for example, if we allow for the idea of complex scalars, all of a sudden we get a very importantly different notion of dimension, right? The complex plane, obviously two-dimensional, it's a plane. Oh, well, but not if you allow complex scalars. If you allow complex scalars, the complex plane has a basis consisting of a single vector and is therefore one-dimensional. Right, so you get this new idea of dimension, which is weird. We also, and by the way, we're going to be thinking about CN going forward, pretty much exclusively. And there are all the stuff that we're going to talk about here. There are variations of these ideas in other complex vector spaces other than CN. We won't be doing any of that in Math 216 at all. So going forward, only CN. So our old formula for the dot product that worked great in Rn, that formula does not make any sense to use as anything that we would even claim to resemble a dot product in CN. As is exhibited by this simple calculation here. Here's a non-zero vector whose, self-dot product with that formula is 0. And that's very much against the rules. And this has a lot of very bad consequences, some of which we're going to see soon. Okay, so we come up with this new formula. This is where we ended last time. This new formula. This is not the dot product. This is a new thing called the Hermitian dot product. And you'll notice the formula looks a lot like the old dot product. And I'm using a notation with the triangular braces that looks kind of like the notation for inner products, which again was modeled off a dot product. So this is pretty suggestive of the old dot product, with the conspicuous difference that whichever vector is on the right, you conjugate. Right? Little change to the formula. Which, by the way, if you want to use this transposed matrix product notation over here instead, again, it's just you conjugate the vector on the right before you proceed with the otherwise typical algebra, and this fixes a lot of problems. This recovers some properties that are, morally pretty much what we need. Something that's going to behave like a dot product to have. So, importantly, you only get 0 with the 0 vector. Right? So, if we were to apply this formula to that vector, we would not get 0. Okay. All right. Now there are a few other consequences of this this little twist on the definition. By the way, terminology, we call this the Hermitian dot product. A couple of consequences are immediate consequences of that conjugation. By the way, it's not symmetric. It's what you might call conjugate symmetric. If you switch the V and the W, You don't get the exact same thing, but you get the exact conjugate of what you otherwise got. Also, if you factor a scalar out of the right-hand side, you get a conjugate. So, in other words, factoring out a scalar is not actually factoring it out exactly. It's when you pull it out, it changes. It becomes C bar instead of C. Okay, so you got a sort of heads up about those two things, but otherwise we have a dot product that largely behaves the way dot products are supposed to behave. And one last observation I'll make. This formula here, this is a formula that applies to vectors on Cn, ordered n tuples of complex numbers, sort of the complex version of Rn. Right? What happens if you apply this to Rn? Right? Let's apply this formula to a vector in Cn whose coordinates are all real. If they're all real, then the conjugation doesn't do anything, and in fact you have the exact previous standard dot product on Rn. So you can think of this as not so much as a change. I guess it's a change in the formula that we've written down, but it's really not so much a different dot product, because on Rn it is exactly the same dot product. It's just a different, you might say, different notation or something. But it is a natural extension of the Rn dot product to Cn. Yeah.
Is Cn number 3 for the first one supposed to have the conjugation?
Great question, and no, it's not supposed to. So what I believe you're pointing to is he's wondering if should there be a bar there, and there should not. The reason why, roughly speaking, this C, what happens to that C in the formula? Well, all the coordinates of CV don't get conjugated, right? And so there is no conjugation happening. Whereas, by comparison, the C on the right, that C, right? You can you can see that is where the conjugation happens. Yeah, great question. Thank you for that. Okay. Now again, we're not gonna go beyond Cn in this class, but there are y'all in other classes very well might deal with other vector spaces that are not necessarily Cn, or other inner products on Cn that behave in the sense of these four properties, like the Hermitian dot product. So any generalization, in other words, of the idea that we just wrote down on the previous page is referred to as a Hermitian inner product. And you'll see those in various different contexts. Okay, moving along. So we've got a new notion of dimension. Right? We're in this new world. We're thinking about complex vectors, complex scalars. The notion of dimension is different. Familiar, but different. We have a new kind of a dot product, which is, it's not that different from our old dot product, but it's still it's weirder in a way, and it's definitely a little bit different. The metaphor that occurs to me on what we're doing here is it's kind of like Alice in Wonderland. There's a lot of familiar sorts of things, but in a weird way, I don't know if it's been a long time perhaps since y'all read that story. I have a 4-year-old, so I've read it recently, right? But it's kind of like that. So here's another weird little Wonderland creation we're going to talk about. We're going to see an Alice in Wonderland version of the transpose. Now, the transpose is a really simple idea in when you're talking about matrices acting on Rn, right? The matrix, just rows become columns, columns become rows. Right? Fine. The formula for the transpose is really easy to write down, but how does the transpose connect to existing ideas? And if I've tweaked existing ideas, if there's an Alice in Wonderland version of something that transpose is connected to, maybe we should tweak the idea of transpose accordingly. So here's the connection. So let me use this notation to represent dot products. It's just inner product notation, but I do that just for momentary future convenience. Let's look at that dot product, and recall that dot products can be written as transposed matrix products. Transposes of products are products of transposes. Don't forget to switch the order. And then I can move parentheses around like so. And what we have here is a transposed matrix product that I can rewrite as a dot product. Punchline, this equaling that, namely that, says that, hey, transpose, neat property of the transpose that we'd never really talked about before, but if a matrix is a factor on the left side of a dot product, you can move it over to the right side of a dot product by transposing it. Yeah, how about that? Right? And a little connection there between dot product and transpose. So now we have this Wonderland version of dot product now, a brand new notion of dot product. Different notion of dot product called the Hermitian Dot Product. Does the transpose, the usual garden variety transpose, have this same relationship? And the answer is no. But there is a different construction that does. And this is called the Hermitian Transpose. The formula for the Hermitian Transpose is this. It's the transpose of the conjugate of the matrix. That's the formula. And that Hermitian Transpose has this same feature. If you are looking at a Hermitian dot product, not a regular dot product, and if you have a matrix factor on the left, you can whip that over to the right by not transposing it, but by Hermitian transposing it, by conjugate transposing it. Okay. This is a very nice exercise for you guys to practice on your own to prove that this works. So take this as a definition and prove that formula. The way you're going to do that, by the way, is you're going to shamelessly copy the strategy that we used up there, showing the connection between the regular transpose and the regular dot product. Same ideas, tweaked appropriately for the new context, right? We have a different dot product, different rules. Write it all down, play the game, and what you'll find is that this holds with this Hermitian transpose. Okay. Terminology very quickly. This thing here is called the Hermitian transpose. It's also sometimes called the conjugate transpose. I think both of these terminologies are immediately clear as to their motivation. Transpose, well, because it's a transpose, right? But then Hermitian, in recognition that this is an alternative version of a transpose that fits, that dovetails nicely with the Hermitian dot product, right? So because of this property, we call it a Hermitian transpose. Or you might say because there's a conjugate in it right there, that'd be a good reason to call it a conjugate transpose. In the terminology, it is also sometimes called the Hermitian conjugate. So I don't know. Anyway, you'll hear that. And another common term is adjoint. Outside of Math 216, that's probably the most common one that you'll see. Okay. All right. So new notion of dimension. A new notion of a dot product. Now a new sort of like corresponding but yet still different notion of transpose. And now what connects to the transpose? I mean, if we modify the notion of transpose, should we correspondingly modify something else that the transpose connects to? And yes, we should. The transpose naturally connects to the idea of symmetry. Right? In fact, that's how you define what it means for a matrix to be symmetric. A matrix is symmetric if it's equal to its transpose. Well, so what should we call a matrix that equals its Hermitian transpose? My proposition would have been Hermitian symmetric, right? along the lines of this pattern. In this new Wonderland world that we're developing, all connecting back to the Hermitian dot product, this is what symmetry turns into. But that's not the term. The term is Hermitian. Anyway, heads up, be aware. That's when you hear someone say Hermitian, a Hermitian matrix, what they mean is a matrix that has this kind of analogous property to symmetry in the Hermitian context. Okay. All right. So, remember, then, a symmetric matrix being a matrix that is its own transpose, therefore has this property. Well, likewise, a Hermitian matrix being a matrix that is its own Hermitian transpose has this property. And surprisingly important consequences of this little formula for Hermitian matrices. I'm going to show you one of them in a couple of moments. So, neat fact, a Hermitian matrix, a Hermitian symmetric matrix, if it's a factor on the left in a Hermitian dot product, you could just whip it over to the right in that same Hermitian dot product. Totally fine. Okay. All right. So, quick observation. Real symmetric matrices are Hermitian. Let me write this down. If a matrix is real and symmetric, well, because it's real, it's equal to its own conjugate. Right? Because it's symmetric, that conjugate is equal to its own transpose. So let's see here, let me highlight. So because it's real, that's equal to that, and because it's symmetric, that's equal to that. So real symmetric matrices, two-step observation, all real symmetric matrices are Hermitian. So that means that all real symmetric matrices have this feature. Real symmetric matrices, you can take them, move them over to the other side, and nothing happens. Okay. All right. So, neat theorem. By the way, a real shocker of a theorem. If you have a real symmetric matrix, now this is, keep in mind, one of the matrices we just talked about, a real symmetric matrix is Hermitian, and therefore you can move from the left side to the right side in a dot product. Nothing happens. And roughly speaking, just because of that, all of the eigenvalues will be real. Now let's take a pause on that before we go along. This is extremely not obvious, right? We've written down plenty of real matrices before. From a real matrix, whatever your matrix is, you write down your characteristic polynomial. The eigenvalues, they're just the roots of that characteristic polynomial. Polynomials have complex roots all the time. This is saying, nope, not if the matrix is symmetric. How does that work, right? What's the connection? How could we possibly... What does the symmetry of the matrix have to do with the resulting characteristic polynomial, and how could we possibly know that? It just seems like a really far out thing to try to prove. And if you were to try to brute force this result, it's intractable. Right? It's a very, very hard thing to prove. By the way, not only are the eigenvalues real, but the eigenvectors are real as well. That's a relatively easy conclusion. We'll get to that second part in a few minutes. I want to focus on the eigenvalues. And seemingly very, very hard thing to prove. Look how easy the result is, though. We consider this expression, where V is an eigenvector. Lambda is an eigenvalue. Who knows? Could be complex. We haven't proved anything yet, so let's pretend lambda might be complex. Well, A is real and symmetric, and therefore Hermitian, and therefore, in that expression, I am allowed to whip it over to the other side of the dot product with no consequence. Okay, who cares? Well, don't forget, V is an eigenvector, so AV is lambda V. The lambda factors out. Yawn. This lambda factors out. Up. Be careful. Real easy to forget this conjugate bar right there. Right? When you factor a scalar out from the right-hand side, you get a conjugate. Right? And now, because of the fact, we talked about this before, but because of the fact that the Hermitian dot product is never zero unless the vector itself is zero, right? That one property, the thing that the regular dot product crashed and burned on, right? The fact that never happens for the Hermitian dot product means that I can cancel this common factor and thus conclude that the eigenvalue is its own conjugate and therefore real. It's a remarkably sort of unexpectedly convenient proof. And sort of mystifying. I think one of the weirdest things about this proof is that, we start off presuming, let's go back to the statement of what we're trying to prove. We start off assuming that something is real. Our conclusion is that something is real. Right? So we have a real starting point and a real ending point, but the way to get from this real starting point to this real ending point is to go through the world, this wonderland world of Hermitian dot products and conjugate transposes. Anyway, very weird fact. Okay. All right. How do you know that the eigenvectors are real? This is a pretty straightforward thing. If the eigenvalues are real, keep in mind, eigenvalues just go there. The way you find the eigenvectors is by just doing a row reduction. And look, if A is real, if lambda is real, this is a real matrix. And if you take a real matrix and row reduce it, I don't think anybody would be surprised that you get all real results, all real null space. It's just, how would we never take square roots when we do row reductions, right? So how could complex numbers possibly come up? Okay, relatively easy part. Okay, next fact, and now I did make some tough decisions, by the way, as to where we are in the course and what we therefore have time to cover. I'm not going to show you this next proof, but it's no harder than the one we just did, but very similar to the one we just did. So I'm going to let y'all read the proof on your own. I just want to state this result. Real symmetric matrix. We already know the eigenvalues are all real. And here's the neat additional fact. The eigenvectors are all orthogonal. That's weird, right? Why would they be? Why would you expect eigenvectors to be orthogonal? You look at two completely different eigenvalues, you're going to be doing completely different row reductions to get down to the corresponding eigenvectors. How would there be a connection between them? It is, again, weird, unexpected result. And it turns out to be true. Now, I do want to emphasize that in this conclusion that these two vectors are orthogonal, it is important that they be eigenvectors with different eigenvalues. Of course, if you look at two eigenvectors with the same eigenvalue, they're in the same eigenspace, and who knows? I mean, there's this whole sort of continuum vector space of eigenvectors with that same eigenvalue. Obviously, they're not all orthogonal to each other. That wouldn't make any sense. And the fact that these two numbers are distinct is part of the proof. Okay, so I'll let y'all read that proof on your own. Okay. A little bit of definition, terminology. Quick reminder, we have this notion of similarity. There's a lot to say about similarity, of course, but we say two matrices are similar if one's a conjugate of the other, or of course vice versa. In other words, if they are conjugates of each other. Okay. So, fine. This is what it means for two matrices to be similar. The similarity comes by way of, what is the corresponding change of basis, or you might say the corresponding conjugation. It is the conjugation. It is the change of basis that makes the similarity happen. just kind of a point of view. So if this matrix P is what realizes the similarity between A and B, the thought is, and this is the motivation for the terminology that I'm about to show you, the thought is that any adjective that describes this matrix P is describing the way in which A and B are similar. This matrix P, whatever property it has, that's telling you about the change of basis that realizes that similarity. So, so the way that they're similar. And so that motivates this term here. So if we have two matrices that are similar, A and B are similar, and therefore, conjugation. Okay, if this matrix P, if the way that we recognize that similarity is by way of an orthogonal matrix, then sure, A and B are similar, but they're similar in a special way, and so we say that they are orthogonally similar. Right? So this is just kind of a refinement of the idea of similarity. A and B orthogonally similar means similar, but more so, not only are they conjugates of each other, but they are conjugates of each other in a special way, namely by way of an orthogonal matrix. Okay. All right, so it's just a little bit of terminology, but it's kind of a subtle motivation for the terminology there. Okay, so analogously, what does it mean for a matrix to be diagonalizable? Diagonalizable means this. It means a similarity. It means similar to a diagonal matrix. So if a matrix is diagonalizable, but furthermore, if that matrix that realizes the diagonalization is an orthogonal matrix, we say that the matrix is orthogonally diagonalizable. And you kind of have to practice saying that phrase because it's quite a mouthful. It's easy to stumble over that. Orthogonally diagonalizable. Variation, orthogonal diagonalization. Right? Okay. All right. So that's what those words mean. And the purpose of this discussion is to just have a convenient way to make this last result here, and that is that every real symmetric matrix. Keep in mind, we already know a bunch of things about these real symmetric matrices. We already know they have all real eigenvalues. We already know they have all real eigenvectors then, as a result. So they have real eigenvalues, real eigenvectors. Wait a minute, the eigenvectors are how you diagonalize. So when we say that we've got eigenvectors, we're talking about how, that P matrix, that will diagonalize it. Right? That's what we're talking about. Well, we know that these real symmetric matrices, we know from the past theorem that those eigenvectors are orthogonal. So we know that the change of basis matrix that allows us to diagonalize is an orthogonal matrix. And so therefore, real symmetric matrices are orthogonally diagonalizable. Okay, so that's this idea up here. Orthogonally diagonalizable. Namely, conjugate to a diagonal matrix by way of an orthogonal conjugation. Okay, how are we doing? Is everybody on board? Okay. There is one detail that I've left out here. I just wanted to get that part done first. What we have not previously known, sort of the missing piece of the puzzle in concluding this result. We knew that the eigenvectors were all orthogonal. What we did not previously know before this theorem was how many eigenvectors there are. Right? And this is constant worry, right? You're trying to diagonalize a matrix. How do you know that it can be diagonalized at all? So the extra information, other than just kind of language and combining previously known facts, the new information being presented in this theorem is, beyond the eigenvectors are real, the eigenvalues are real, the eigenvectors are all orthogonal, is that the eigenvectors are as numerous as you would expect. There are no missing eigenvectors, etc. Thus, diagonalizable. Okay. All right. Variation on this theorem. This is a really neat theorem. By the way, again, not going to prove that result. It just takes a little bit of time to go through the details to see that, there are no missing eigenvectors. If you're curious, come talk to me. But it's beyond what we can reasonably do in Math 216. So here's a variation called Schur's theorem. If you have a matrix with all real eigenvalues, then it is, what are we going to call this? Orthogonally similar to an upper triangular matrix. Let's see. Well, similar to an upper triangular matrix, you might call upper triangularizable. Right? Just kind of working with the analogy of how we've defined terms in the past. So orthogonally similar to an upper triangular matrix, you might call orthogonally upper triangularizable. Right? So what this theorem says is that you get that result if the matrix has all real eigenvalues. Now, how does that relate to this original theorem up here? Well, it's depending on your point of view, either a weaker result or a stronger result. And let me explain what I mean by that. Let's look at the assumptions here. This first theorem assumes that your matrix is a real symmetric matrix and therefore has all real eigenvalues. Schur's theorem only assumes that you have all real eigenvalues. Might not even be symmetric, as long as it has all real eigenvalues. So what we have here, Schur's theorem has a weaker hypothesis. That means that Schur's theorem applies more broadly than the theorem above. And in that sense is a kind of a stronger theorem, right? The above theorem applies only narrowly, just to those symmetric real matrices. Okay. All right, so is Schur's theorem stronger? Well, here's the thing. Schur's theorem only gives you orthogonal upper triangularizability. The theorem above gives you even more. The theorem above says not only is it orthogonally similar to an upper triangular matrix, it is furthermore orthogonally similar to a diagonal matrix. That's a stronger conclusion. So in terms of the conclusion that you get, Schur's theorem is weaker. In terms of the breadth of application, Schur's theorem is stronger. So, again, points of view. Okay. All right. So, this is all we are going to talk about in 9.3. There's another page of notes here. This really does take some discussion, and this is kind of supplemental. It's not something we really need to do. Given that we are behind schedule, I'm going to axe this page, so you're not responsible for anything on this page. If you want to give it a look, feel free. If you want to ask me some questions about it, you're very welcome. Future reference, if you ever hear anyone talking about a unitary matrix, right? FYI, a unitary matrix is just a Wonderland alternative, sort of a Wonderland version of an orthogonal matrix. That's all it is. It's basically saying orthogonal, but in that Hermitian context. So anyway, refer back to this page if you ever find yourself interested in unitary matrices. Okay. Otherwise, feel free to skip this page. Okay, so that does it for chapter 9. We are now going back to chapter 6. This is our last chapter. Oh, hey, by the way, we are also now out of the linear algebra portion of this course. We are all differential equations from here on out, with one asterisk. The big asterisk, of course, being that the reason that we learned linear algebra, well, one of the reasons that we've done linear algebra up to this point is so that it would help us solve differential equations. So, yes, we're going to write down a bunch of differential equations here. We're going to solve the differential equations, but we're going to be using linear algebra to do that. But we're not learning any more new linear algebra to speak of. Okay, all right. So here's what we're going to be doing. There was a target for Chapter 4, you may recall. In Chapter 4, we were looking at nth order linear differential equations. And most of our time in Chapter 4 was spent looking at nth order constant coefficient linear differential equations, right? So it's a very restricted category of differential equations. We talked about how linear algebra was a powerful tool in addressing that specific kind of differential equation problem. Here's our new target. This is a new kind of, you might say, differential equation. This is actually a system of differential equations. You'll notice there's several equations here. There's a whole bunch of equations. Here's the really good news. First order. Only one derivative. That's it. Right? First order. My gosh, how hard could it be? It's just first order, right? I mean, my gosh, we kind of blew past Chapter 3 in this course because, well, it's just first order. You know, how hard could it be? We are going to find that there are some challenges with this kind of system. So this is not going to be trivial. This is going to actually be fairly sophisticated. But nevertheless, hey, still, you got to put this in the win column. It is just first order. So let me talk about why these are hard. The temptation would be to say, well, fine. So you've got a bunch of differential equations. Okay, cool. Solve them one at a time, right? Just divide and conquer. Let's look at this first differential equation. Let's solve that first. We'll solve for y1. And then we'll subsequently go on to solving for these other functions. Here's the problem. I can't solve for y1 yet because I don't know yn yet. Why don't I know yn yet? Because I haven't gotten to that equation yet, right? If I do this one first, I don't know one of the participants in the equation. I don't have a well-defined question. This one equation by itself is not a well-defined question that I can deal with. I would need to know yn. And so you say, fine, well, then let's do this one first. We'll solve this equation first. We'll figure out that yn, and then we'll plug it back in and proceed. Well, of course, the problem here is I don't know y1 yet because I haven't solved that equation yet. This is a nasty little problem, right? I can't take this system of differential equations and sort of separate it out into n separate equations that I deal with one at a time. They are unavoidably linked and tied together. I'm going to have to find a way to solve them all together, not just one at a time. Does everybody see why that's ugly? Well, it's like not clear what we're gonna do with that. Okay, so first observation I want to make is largely notation, but this is an important thing. Notice that if you were to take all of these coefficient functions and make a matrix out of them, and if you were to take all of these variable functions that we're trying to find and make a vector out of them, and if you were to take all of these sort of right-hand side terms and make a vector out of them, then notice that the whole thing, right, this entire system all simplifies down to that one equation. It is a neat fact that, using matrix and vector notation, right, this matrix, here let me color code, this matrix A times this vector of functions y plus this vector of functions g, ay plus g generates what you might call the whole right-hand side of that system. Everybody on board with that? It's kind of a matter of multiplying this out and observe that you get that up there. Yeah, please.
What is y a function function of?
Yeah, right. Okay, so y, all of the y variable functions are functions of x. So here, let me squeeze that in here. So y1 is a function of x, et cetera, et cetera. These are functions of x, so y1 prime is a function of x. Yeah, right. So as usual with differential equations, we're looking for a function of a given input variable, and all of these given input variables are all the same. So x, these are all functions of x. Yeah, very good question. Yeah, thank you. Anybody else? Okay, well, so we're going to develop a little bit of context first, a little bit of terminology to start off with. This will seem a little weird. I'm going to refer to this as the right-hand side of the equation, and if you, point of order, that's not the full right-hand side. Yeah, sure, but look at this. I could rewrite this as y prime equal minus, come here, eraser. There we go. Minus a y equals g, and now this is the right-hand side of the equation. So, reasonable question then. Well, why didn't I write it like this in the first place, right? I mean, when we were in chapter 4, we had all the y stuff on the left and all the not y stuff on the right. This seems like a pretty reasonable way to write the system. Why didn't I write the system like that over here? And there's a great answer to that question that we'll get to in a little while. But for the moment, it ends up being convenient sometimes to write it like this, and sometimes to write it like this. In this case, interpreting, making sense out of what this g is, thinking of it as the right-hand side, it makes sense to think of it, the equation in this form. So, as usual, when the right-hand side is equal to 0, we call it a homogeneous question. This being a system of equations, we call it a homogeneous system. Okay. Initial conditions, right? We remember initial conditions from chapter 4 and chapter 3 even. And this is just like in chapter 3, really. If you have a bunch of starting values, and keep in mind, y is a bunch of component functions. This y vector, it's a y1 function, a y2 function, etc. If you have starting values in a vector b, starting values for all of those component functions, we call that an initial condition, and we call the resulting differential equation an initial value problem. Totally analogous to in chapter 3 and chapter 4. Okay. All right. By the way, I want y'all to be on the lookout as we go through this stuff. A little bit more today, and then quite a bit more for the next several days. There's a very strong analogy between ideas that we saw in chapter 4 and ideas that we're about to see here in chapter 6. It's hard to see this coming. But there's a strong connection between, let me think now, chapter 4 was nth order linear differential equations, right? What are we doing here in chapter 6? Well, it's not nth order anymore. Here in chapter 6, it's first order, but systems of differential equations. So we have these different kinds of annoyances, right? It's annoying to have a high order equation in chapter 4, and it's annoying to have a system in chapter 6. But despite them being very different kinds of questions, it turns out that there's a strong connection between how we attack them. So anyway, heads up for that. First example, we have an existence and uniqueness theorem for these systems, just like we did in chapter 4. So, certain regularity issues being acknowledged. So, if your coefficient functions are all continuous, and if your right-hand side functions are all continuous, then initial value problems, solution exists, and solution is unique. So again, I like to call this an existence and uniqueness theorem. And This is going to be the cornerstone of everything that we're going to do in Chapter 6, in the sense that now we at least know that we're not looking for something that isn't there, and that we know that once we find a solution, we know we're done. We know that there isn't some other solution out there that we just didn't kind of happen to think of. Right? But very important that we have this. Right? Again, not going to prove this in Math 216. Okay. All right. Now, a couple of observations. We're going to look at homogeneous cases first. So this is the homogeneous equation. What does a solution look like? What is this thing? Well, it's a vector-valued function. It's you might say, a vector made up of a bunch of functions. Same thing. Okay, well, reminder, when if you have something like this, where each one of these things individually is in R, then we refer to the whole thing as being in Rn. Right? If you have a vector of components, the components are all in R, then we say the vector is in Rn. Well, analogously here, these components here, individually, are all C1. Right? They're all continuously differentiable. And therefore, the vector, by analogy, we're going to say is in C1 in. Right? The in exponent representing that we're talking about vectors of ordered n tuples of these things, and these things all being C1 functions. All right. So anyway, you can think of this as just notation, but the more important thing to recognize from this is that what we're talking about is these things that we're looking for, the solutions that we are looking for, are in a vector space. This is a vector space. The collection of all vector-valued functions such that each of the blah, blah, blah. Not hard to show. This is a vector space. Okay. Here's another thing. We're looking for where this is equal to 0, right? So we're, again, homogeneous at the moment. Considering the homogeneous case, we're looking for where this calculus here adds up to 0. And that means that what we're looking for is the kernel of a linear transformation. Now, slow down. How do we know that this is a linear transformation? That is something that y'all need to check, and I want to encourage y'all to do that. Confirm for yourself that this formula right here, L of f, defined by this formula, it's f prime minus af. Straightforward calculation. Confirm that this is a linear transformation. But it is, and y'all are going to confirm that for yourselves, and therefore we're looking for a kernel. So here's the upshot of this page. The upshot of the sort of second half of this page is that, like in Chapter 4, let me just remind you, in Chapter 4 we started off doing kind of, you might say, hardcore calculus. Here's a differential equation, and we want to solve, we want to find these functions. It was all very analytical, right? And then we realized, okay, yeah, but we're looking for vectors in a vector space, and it's use linear algebra tools and dimension and this kind of thing. We basically use linear algebra. We rephrased the seemingly analysis question as a linear algebra question, then we solved it with linear algebra. And the same thing's happening here. Sure, we're looking for, system of equations, derivatives, functions, all that analysis stuff. But the very important point of view to take is that we are looking for the kernel, that's a linear algebra concept, of a linear transformation, that's a linear algebra concept, defined on a vector space. Right? Linear algebra concept. So it's kind of concealed But this analysis problem is really a linear algebra problem. And linear algebra is going to be the answer that makes us, that allows us to actually get answers. Okay, so good stopping point for today. See y'all Wednesday. Have a good one.